Welcome back everyone, Mr. Allen here. Going to take a minute to review some of the things we saw when we first looked at trigonometry. As we moved from our first day, remember our first day we basically just looked at tan and we talked about rise over run. And that worked pretty well for most of what we did until we started seeing our triangles in a different orientation. And then you had to recognize that in this case, the rise was this side over here and the run was this side here. And of course, the more confused this gets, the more difficult it might be to recognize where the rise and run should be. So we came up with some new terminology. We knew the hypotenuse already from, well, years ago. Hypotenuse is the side on the right angle triangle across from the right angle. It happens to be the longest side, but the definition really is this. So it's easy to establish. And then as I walked around the room, I started asking the question, who's on the opposite side of the room to me right now? And we all recognize that the opposite side of the room is always all the way across. And so looking at a triangle, we use the word opposite to indicate the side that is across from the angle we're looking for, or the angle we know, depending on what type of question it is. Okay, so here is the angle that I'm dealing with. The opposite is over here. Hypotenuse is already established, and so the third side is the one we call the adjacent. And the adjacent, by definition, adjacent means beside. So it's the side beside the angle I'm interested in that isn't the hypotenuse. Okay, so up here, if I'm looking at that angle, then the opposite becomes the side over here. Adjacent is this one, and hypotenuse, of course, is always the same as it was. And just some examples here, just for a little bit of practice. Finding the angle that we're looking at. There's the X, there's the Y, there's the Z. And again, the opposite is always clear across the triangle. The hypotenuse, not very well drawn on this one. The hypotenuse is, or should be fairly obvious to you. And then the adjacent is the other side. Across from the Z is the opposite, adjacent is here. And so just a bunch of practice examples there. And of course the last step is then actually making use of that information to do some calculations. So we saw SOHCAHTOA, and again, Scott's old Honda can accelerate higher than other automobiles. It was given to me by one of my students once upon a time. It helped some people. We need to be able to know this, so somehow you have to remember that. And what that tells us is that the sine ratio is equal to the opposite side divided by the hypotenuse. The cosine ratio will be equal to the adjacent side divided by the hypotenuse. And tan is equal to opposite divided by adjacent. So when I look at a triangle here, I have an angle that I'm interested in finding. Given that angle, I need to know what information I have throughout the triangle. Well, I have this 12, I have this 15. The 12 is my adjacent, the 15 is my hypotenuse, and so I want to use the ratio of these three that deals with the adjacent and the hypotenuse. So we always want to remember that if there is a single variable in an equation, we can solve for that variable. I can collect like terms if I have several x's in an equation, I can collect them, get down to the point where I have some number of x's equals some value. I can divide through by the coefficient and solve for x. But as soon as I get a second variable or second unknown in my question, I can no longer solve that equation with just one equation. So here, having an unknown angle, I want to use two known sides. So the 12 and the 15, adjacent and hypotenuse, tells me that I'm going to do the calculation involving cos. And I always suggest you set it up properly. Cosine of the angle I'm working with is equal to the adjacent over hypotenuse. 12 is my adjacent, 15 is my hypotenuse. If I knew my angle, I would plug it in instead of one of those. And then once I've done that, do what I need to solve it. In this case, I have a ratio for cosine. I need to find the angle, use the inverse. And so I'm going to use the inverse of cos with this ratio, and I find that my x value, my angle in here, is approximately 37 degrees. Similarly, moving forward here, I have an unknown angle here. I have an opposite and adjacent that I can work with. So tan, because tan works with opposite and adjacent, tan of the y value will be the opposite divided by the adjacent. Numbers in. To find the angle, use the inverse. And 49 degrees. Now looking at this third example, you can see that it's a little different in that there's a side that I don't know and an angle that I'm given. So just like in the other two where I started from an angle, I'm starting here from an angle. This time it happens to be an angle that I know as opposed to an angle that I want to find. From this angle, this is my opposite, this is my hypotenuse, and of course sine is equal to the opposite divided by the hypotenuse. So because I have an opposite and a hypotenuse that I need to work with, I will use sine of this angle. So sine of 20 is the opposite over the hypotenuse. The z value is the opposite that I don't know. The 42 is the hypotenuse. And now it's a matter of rearranging an equation just like I would with any other equation. If this were 5 equals z divided by 42, we would multiply both sides by 42 to isolate the z. So I'd have 42 times 42 times 5. Now I have 42 times sine of 20 equals the z value. And you punch that into your calculator, again, depending on the type, in exactly the way you would expect. 42 times sine 20 equals, or 20 sine times 42 equals, and you should get 14.4. Last sort of unique type of question, and it's not that unique, but it's a little different. I have, again, a similar situation here. An angle is given to me here, and so from that angle, opposite hypotenuse. When I set up the ratio, though, you see that I have sine of the 15 is the opposite divided by the hypotenuse, and now my unknown value is in my denominator. A little bit of a pain. I need to isolate x, and so I can't have it in the denominator. I'll need to multiply both sides by x in order to ensure that it's not in the denominator. So I have sine 15 times x, 45 divided by x times x, and of course what happens is when I divide by x and then multiply by x, these two things just divide each other out. This is essentially 45 times x divided by x. This is a 1. And now I have x times sine 15 on the one side equals 45. If this were something else, something like 5x equals 45, we would divide both sides by 5 and end up with x equals 9. And so in exactly the same way, we divide both sides now by the coefficient essentially that I don't want, the sine 15, divided by sine 15, and we get 173.9. The others should all be sort of just either special cases or repeats of the questions above. In this case, you can sort of see the math you've learned before doesn't disappear. And so in this question, we had a 27 length here, a 45-degree angle, and a 90-degree angle. If you recognize that the three angles must add to 180, then these two are 45. That means it's an isosceles triangle. And the third side here, the z side here, is 27 as well. If you didn't recognize that, of course, you could then do the calculation exactly as you did in all the others, and we get the same answer. And then the last three questions I gave were sort of variations to make you think. This one was simply asking for the missing angle here, similar to above. I have a 90, a 30, and a unknown. Subtracting makes us a 60. The 100 on the side doesn't make any difference at all. This was kind of a unique question in that when we tried to solve it, of course, we got a math error. And the reason for that, if anybody missed it, the hypotenuse here is labeled as 36. The opposite is labeled as 45. But we know that for every right angle triangle, the hypotenuse has to be the longest side, which means that essentially this diagram is impossible. And then of course the last one here, if you sort of notice that there's no angle given to you, but you have two sides, you can always find the third, knowing that it's a Pythagorean theorem from way back as well. So the keys to the trig stuff we know so far: to find the angle, use the inverse is the first key. The second key is that we always start with an angle. It's either the angle we're trying to find or an angle we know, and from there we establish where our opposites, our hypotenuse, and our adjacent will be. And then finally, once we know that, we can use SOHCAHTOA to determine whether we want to use the sine ratio, the cosine ratio, or the tangent ratio. And after that, it's just a matter of writing the ratio down, writing the equation down as a ratio, and solving it.